Central, congrats on the first. Zach, with a quick math. I think the double factorial means odd, like you go by every odd number, right? Let me turn the YouTube stream on before I forget. Oh, I did do that. Look at me. So 5 times 4 times 3 times 2 times 1. Slim, thank you so much for the raid. I hope your stream was good. Welcome in, everyone. We're about to get started doing some general relativity reading group discussion, problem solving, stuff like that. Femlox, hey. But I'm just doing a quick math from Zach. The ones technically cancel it, who cares? So I think I just get 8. But yeah, this little I think it's called a double factorial. GG's. All right, sounds like I got it right. You ready for the slaughter? Me too. that double factorial just follows along odds if it's an odd number or evens if it's an even number. Anyway. Better than a day to the beach. Nice, nice. Okay, I think everything is going. Hey, Mathesix. Okay, I'm gonna hop in Discord. And so this is our first meeting on Chapter 5. Chapter 5, we're not even into the actual general relativity yet. We've only been doing the prerequisites, but we're nearly there. This is the last chapter before we actually get into the actual general relativity. Hey, Fembucks. Looks like you're still muted.
Yeah, thanks. I was muted.
Okay, nice. How's your Saturday going?
Ah, pretty good.
Nice.
Pretty good.
I
feel like I don't know enough special relativity, but other than that, it's pretty good.
I think it's about to go a little bit worse depending on how this goes.
Yeah.
Yeah,
I got a little more than halfway through chapter 5, and then I sort of just tried to skim the rest of it because I felt like I had lost the thread of what was going on.
I feel somewhat similar, yeah. I think I understand at least mathematically where a lot of things in the first half come from, but I'm pretty confused on how we're going to use them. I guess that's part of the fun, though. I guess let's start scrolling through it. There's definitely quite a few things that I felt weird about. I remember I need to find it. For the first thing that was weird was this convention with the indexing.
Yeah.
I'm trying to find the actual statement that, okay, yeah. So on page 80 at the bottom, equation 511, they give an expression with 2 different Greek letter indices, and they say it's a double sum, 1 over alpha, the other over beta. But I don't think it's a double sum as in like 2 capital sigmas, alpha equals 0 to 3, beta equals 0 to 3. I think they're being incremented like I misinterpreted that statement at first. I guess maybe I should
Oh, yeah.
Right at
Are
what
you
I mean
saying
in
there's
scale drop.
three terms instead of 9 terms? Or would it be 4 terms
I guess
instead
4
of 16
if it's 0 to
terms?
3. I think it, yeah, I think it's not a double summation as I would think of it. Okay, so that's how they seem to be using it throughout the rest of the chapter. We're like,
yeah, I was thinking of it as 16 terms, I think.
Okay, so I'm not the only one who felt like that. Alpha equals 0 to 3. Hey, color cone. Beta equals 0 to 3. Oh, and it's gonna be difficult to write four vectors. I think they're saying to do an underline thing for four vectors.
Yeah, they said underline, and it has to be wiggly.
Yeah. So when they said the double sum, I interpreted this where you have to you take beta equals 0, and then you do every single alpha 0 to 3 with that beta equals 0. But I think what they mean is you're incrementing them at the same time. Where you only get the pairs. It's like 0, 0. Or maybe, oh, maybe it doesn't matter. Oh my god. Uh, like, I think it comes out to be the same thing because E1 dot E0 is 0, right? These are orthogonal. Maybe I've been worrying about nothing. But are they generally orthogonal?
I don't know.
Imite, I'm not going to be doing math help for about 2 hours. I'm not quite sure how to do that problem either. Actually, they say that's for general vectors, though. I think E is implied to be orthogonal vectors. Did they say that though? That'll make me happy if they did. Hey, G-Ive.
Yeah, maybe the last sentence on the bottom of page 80. Scalar products of basis 4 vectors that point along the orthogonal coordinate axes of an inertial frame.
Okay. Yeah.
So that means they do have to be orthogonal.
I think so. I mean, if it is actually a double sum, I think they have to be. Otherwise, it's not going to come out to be how we want it. Like we only want Tuff is referring to the full 16. Okay, FizzBuzz. Pearl's going to relax your orthogonal relation later. Okay, thank you, FizzBuzz. So E alpha dot E beta can be an interesting 4x4 matrix. Yeah, it did feel weird because they later on introduced this eta matrix that's just kind of a diagonal matrix that maybe is neat but doesn't seem to do that much to me yet. But okay,
Yeah, is this eta alpha beta? Eta alpha beta, is this like set in stone, or does it depend on what the problem tells us? It does say
uh,
above that the scalar product of all vectors is fixed once the eta alpha beta are known.
yeah. So I think it depends on what your basis looks like, and we're working with nice orthogonal bases, and BizBuzz might be saying that we're going to eventually have non-orthogonal bases.
Yeah.
Okay. That helps clarify that then. Um, and at least for the next, I know I'm gonna like it's. I think it's gonna be a really easy mistake to make with dot products that the first component needs to be negative. That's gonna be an easy thing for me to forget, I think.
Yeah.
But I think I was kind of mostly okay with the next few pages. The velocity 4 vector, or the 4 velocity. There's some weird things with this though. Like the fact that it's normalized, but to -1 feels very weird. When I first read that, I'm like, so can our velocity only ever be 1? But I think that just because when you include time as a dimension, It's just weird, I guess. Hey, Tyler. But yeah, the four velocity being a unit vector is very weird to me. Hey, Dumod.
Yeah. Is that because we let C equal 1, maybe?
Oh, it's possible that like a c squared or something would show up in non c equals 1. Not for like 2 hours or so, Dumod. But that must be because I think that's being because of the time component just kind of makes it normal. And Kayla Astronomy, hey, well, welcome in. This thing that I do on Saturdays, uh, where we read through this book, Gravity by James Hartle. And right now I'm in Discord with Fembox Fan. Thank you for the follow. And we're just trying to learn about general relativity. We're both learning this for the first time. Yeah, there's Fembox there. And so Fizbuzz, who's in chat and also streams, will pop in and help us. And then we also have Dr. Cook, who periodically pops in and helps us as well. But yeah, we're learning this for the first time. We're still on the prerequisites for the actual general relativity, but we're nearly there. Oh, nice. In high school. That's impressive. So yeah, we just started in chapter 5. We're just kind of discussing the content, and then we're going to get into problem solving. Hey, Jed. Okay. Hey, Andrew. I'm good. How about you? So yeah, a lot of the stuff I feel like there's some interpretation with like why the four velocity looks like that it does, but I don't know. I'm just kind of accepting it. University preface class office and PhD in physics. Oh, nice. Fizz was saying, think of it like a choice. Like if I wrote a simulation where we solve for functions t of sy, x of s, y of s, z of s, we could reparameterize the curve however we want, but choosing u squared equals -1 gives us a choice of parameterization.
Oh.
So, but this followed from something else.
Oh,
I guess from
because they were
parameterization in
talking
tau.
about, yeah, equation 521.
Right.
Because they did say they were going to use sigma as a parameter, and then they said, well, let's just use proper time.
Okay.
But then I know later on in the chapter somewhere they brought sigma back. I think when they were doing the Lagrangian stuff.
Oh yeah, you know what? I think I remember in like in calculus, it's somewhat common. I don't think it's always taught, but like they sometimes make students calculate the arc length of a curve and then parameterize the function in terms of arc length rather than in like t.
Yeah.
That might be a similar idea.
Arc length parameterization. Yep.
Hey Ashley. And tau is
Example
just the arc length, I think.
5.3 felt like that. That
Just saying
example on
exactly.
page
Okay.
83.
5.3. Yeah, they are doing exactly that.
Yeah.
Okay. Scrolling through. Oh, okay. Page 86, equations 5.38 and 5.39. Uh, I was having a very hard time figuring this out. I think I have figured it out now, but it's not as direct as the book makes it seem to me, at least. Where they find, or primarily they find y f dot u equals 0.
Yeah, that felt weird.
Um, cross multiply, it's always bigger. Uh, it's more like 1 divided by a very small number is a very big number. If you cross multiplying with that, I think something's gone wrong. 5.39, yeah, that does check.
All right, F you. There it is. Yeah.
Yeah. I asked physics depression about this equation. I was like, oh man, I hope he doesn't think that I'm a troll right now saying F dot U. Yeah. But the way that I was interpreting how they got this, starting from 5.35, they have M du, is it d tau? Yeah, equals F.
Maybe I'll mention, I think in the list of corrections for the textbook, I think they talked about these two equations.
Oh, really?
I
I
think
should pull that up.
so.
I got it somewhere here. I haven't been good about checking the corrections. What page is this? 86. Oh. Okay, after 5.38, this is the exact equation. Oh my god. Which from dot 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 or, which from 5.36 implies u dot a equals 0.
I mean, I guess they didn't change it too much, but it might make it clearer.
7. Kinda. I think I still would have had my same issue.
How did
But
you do it? Did you use a product rule?
so I didn't know that existed for dot products. That's the thing that I was confused about. But yes,
Okay.
that's what you have to do, I think.
I think
Thank
yeah,
you,
I've seen
Andrew.
something similar to this. Um, yeah, what's the problem I'm thinking of? When you've got like uniform circular motion, like you've got um, you're swinging a rock around on a string above your head, and if it's going at a constant speed in a circle, then if you forget about the gravity, then at every instant the tension force, what is it? The acceleration is always at orthogonal to the velocity, right? So you can say like, how does that work? So it's ddt of v dotted v equals 0 or something. I think
Okay.
that's what it reminded me of.
Yeah.
That's like velocity and being orthogonal to acceleration. And here it feels like they're saying the force is orthogonal to velocity or something, which felt weird.
Um, yeah. And so there's a problem exactly where they make you draw some acceleration for vectors that might help. Actually, I think I heard of that. Yeah. What I thought they were doing with this, like, I thought they were starting from the F equals MA thing, and I thought they were dotting each side with U. Uh, they're not, I don't think, but I thought that they were doing that, and then somehow saying that like you can randomly draw in parentheses to make it U dot U and then derive it on the outside. But I think that's completely wrong. All right, I think that's like valid. All right, see Ashley.
Maybe
How,
you can kind of do that because
oh,
what do we know? We know the dot product is commutative. So you just get a factor of 2, wouldn't you? Like if you multiply both sides by 2. But I guess then you do have to use a product rule, don't you? I'm
or
thinking of the product rule.
yeah, so like I think going at it like this though is wrong because I think that this dot product is different from, like, a derivative dot with the original is different from the derivative of the dot, if that makes sense.
Yeah, yeah. No, I agree. I
Okay.
agree.
And so I think what they did instead is they just decided to start with the statement uh the derivative of u dot u is 0 because we know that u dot u is constant. And then you can multiply each side by m. And then you could do the product rule on that dot product. And then you get a factor of 2 that you can divide out, but that's fine.
Yeah, that's what I was thinking too.
Um, so yeah. So yeah, that will become the a dot u 0. Okay. Or I guess m dot u or f dot u. Oh yeah, thank you. So yeah, I was stuck on that little bit there for a long time. Um,
So what were they trying to, what was the big idea they were trying to show us? They were trying to show there's 3 independent equations instead of 4.
yes, which I'm still not completely clear on what that means. I think it means that if you know 3 of them, you can always calculate what the fourth must be because of this.
Hmm.
But I'm not sure if I'm thinking about that the right way. um, and then getting into the energy and momentum stuff. I'm confused on why the time component of momentum is energy. I can accept it, but it seems like it kind of pops out randomly, and I feel like it's probably not random. But
They
it
said the
would
1/2 mv squared is kinetic energy,
right.
and then
It's only for small velocities, I guess. But come on.
yeah, at small velocities, pt, at small velocities, p superscript t reduces to the kinetic energy plus the rest mass. Hmm.
Yeah, so I was in that they call it energy though without reference to velocities being small as well. So I wonder. I feel like maybe I'm missing a piece there with why is it. I get why it's energy for small velocities, why it's still energy for big velocities. Maybe that's like a unit, like a dimensional analysis thing, though.
Yes, this was the next page was really where I lost track of what was going on, but I was already over my head here too. Yeah.
Yeah,
I mean, like just below that, they're talking about E equals mc squared
that was cool. I was like,
for a particle at
yeah,
rest. E equals mc squared in the more usual units. So there's an invisible c in here somewhere as well.
yeah. I was kind of happy that once I saw equation 5.47, I was like, oh, that looks kind of like E equals mc squared if the c is gone because we're letting c equal 1. And then I read the sentence like, oh, hey, I guessed right. Um, but yeah, then things got
Yeah, this is
really
where it
weird.
got ugly. 5.49. I had lost any idea of what was really happening when I looked at 5. 0.49.
Yeah, I don't think I ever figured out how they got that F dot V for the time component.
No, me either. A 4 force in terms of a 3 force. And they said the 3 force is the time rate of change of the 3 momentum. I guess we call that the 3 momentum, do we?
Mm-hmm.
The P with the arrow.
I think so. Yeah, I assume saying through momentum. It was interesting that that comes out to be the power. Um, because force times velocity.
Oh, yeah.
They said it's a familiarization from Newtonian mechanics, but they didn't say what it was. That kind of annoyed me. Like,
Yeah, I was confused too. You just told me it's power, and I'm like, oh, okay. Yeah,
yeah,
that's how it works, isn't it? Time rate of change of energy.
I only noticed it because of the left hand side there.
Yeah.
I haven't seen it with like vectors with a dot product like that. I just kind of assumed that's how you define it for multiple dimensions. Um, I guess that makes sense for a dot product given how work is defined. Yeah. Um, Durbob, isn't F frequency very often in physics? And generally, yeah, for anything that's like oscillating, we do talk about the Doppler shift in a little bit here, if that's what you're talking about in particular. Oh wait, you're talking about like F as a variable? Uh, Usually I see omega, like Greek letter omega for frequency. In this book, we're using lowercase f to mean force, but in special relativity terms, which is a little bit different than regular Newtonian terms. Um,
Yeah, there's a lot of new notation to catch in this chapter.
yeah, essentially
Did you
just like,
understand this
oh yeah,
example on F equals QVB?
I could kind of follow. I don't think I could do it for myself, but
Hmm.
thanks for the follow, Durbob. Hey Matthew. Um,
I don't think I understood where the gamma showed up in 553.
the gamma.
Yeah, where'd they get that gamma in the numerator? Oh, maybe it's from 549 where they say the space component of the 4 force is gamma times the 3 force.
Um, Simply facts hate. Relativity's yeah, we're really this chapter is on a different level, Matthew, of being hard. The It's a mass times acceleration, and I think the gamma. Why are we involving the gamma?
Oh, wait.
Oh, it's just the maybe it's the right side of 5.52.
Yeah, that's what I was about to say, because there's a gamma there, isn't there? It's like m gamma times dv dt.
Yeah,
Is that what they did?
I think it
Oh,
must be.
yeah, you got it. That's what they did.
And then the right side is 5.51, or like just the regular Lorentz force.
Oh, yes. Okay, thank you. Yes. I get it now.
Huh. Kinetic energy.
All right.
Oh, it's probably
So
relation
then
there,
they could
Matthew.
get the radius.
Right. They notice that there's the magnitude of momentum hidden inside there, which seemed tricky to spot. Um, are we studying for school? No, this is just for fun, Bob. Fun
You
and
know,
profit.
it's gonna be tricky to keep track of because sometimes they list them out as four components, don't they? But then a lot of times it's two components. Like they give you the time component and then like the
Just the
3D space
X.
component. Yeah.
Yeah, I guess to keep it simpler, but I assume we're not always going to be able to restrict the motion to one dimension.
Yeah.
It's a little
Yep.
too convenient. Because positions have big relativity, yeah. Um, hey, Anonymous. Can I come fix your car in the middle of the highway? No. I don't know anything about cars. Um,
And then we're back to the Lagrangian again.
yeah.
And they said this is going to come back in chapter 8 on GeoD6.
Oh, I think so, yeah. The Lagrangian's so high. Lagrangian is confusing so far.
Yeah, this page here, page 90, I didn't read this very carefully. I just sort of said, okay, let's move on.
Yeah. Oh, nice, Sage. Good luck.
Did
Yeah.
you read through that? Did that make sense to you? I didn't understand equation 560. They said x1 equals x.
Oh, this part is definitely weird. What was happening here?
Yeah, look at 558. Look at 558. So we're taking the derivative with respect to sigma of the partial derivative of L with respect to one of these suckers inside the fractions. It's like it's a derivative of a partial derivative of a derivative or something.
Yeah.
With respect to a derivative, right? Like one of our coordinates in this Lagrangian is one of these derivatives.
Yeah, this is it's so confusing to me that Lagrangian is a function of other functions. Um,
I do think some of this is supposed to be a little bit of a background.
yeah.
Like I think we're supposed to have some understanding of Lagrangians by the time we hit this course. Yeah.
Is D from integration? I'm not sure. There's a whole lot of D's on this page. So I'm not sure which one you mean. um, but yeah, the Lagrangian is just I did figure this out at the time that I read it. The Lagrangian only depends on the derivatives with sigma. It doesn't depend on the original things. So the second term in 5.58 is 0.
Oh, damn it. There you go. That's where it went.
Yeah.
Oh, thank you. Thank you.
Um,
Oh, and then if we differentiate that thing, we get because it's no, no.
the oh, you just have to do the annoying hard work of differentiating the square root of basically 1 minus
Yeah.
x squared. But that's
Okay,
why
so where did
the 1 over
the
L,
twos cancel? The twos cancel. I see it. The
yeah.
1/2 and then the 2. Okay, thanks. I see it. Yeah, I should have looked at this a little more. but I was a little bit disheartened by the time I got to this page.
Yeah.
So I said, let me see if I have more luck with the light rays section. But alas, I didn't.
dx. X here is actually just a function uh, for position or for time, confusingly. General type is usually taught differential geometry. Yeah, they've given us a crash course in differential geometry. Um, I never actually had taken a class in it though.
No, I didn't take it either.
But yeah, so they only do the calculation for x1, but they make the point that it's the same for the other three coordinates also, I guess.
Yeah, I'd buy that.
There's a tech there. I guess there wouldn't. I guess the sign issue wouldn't matter for the time component. The sign would be flipped, but it's equal to 0 anyway. Um, worst class you took ever? Oh no. Means to do 30 page. Wow, that's saying a lot, Matthew.
So that's probably really important. They say the world line of a free particle in flat space-time is a curve of extremal proper time.
Right.
That's the last sentence there, yeah.
And that's the longest time. That's just like the vertical straight line, I think, for a free particle. And I guess that's what they're saying extremal, because in Newtonian physics, the extremal time was the minimum, the straight line. So depending on your space, it could be the minimum or the maximum, or maybe it's saddle. No, a saddle point can be extreme. A great class in a masochistic kind of way. That's what these reading groups are, just an exercise in masochism.
Yeah, they said the straight lines along which free particles move in space-time are paths of longest proper time between two events. And they said that towards the start of
Oh,
that section.
really? Because I thought those had zero length in space time.
Okay, so here's a question. The straight lines along which free particles move in space-time are paths of longest proper time between two events. So,
Well, no, wait, we can't use proper time for a light ray. They're saying that start of paragraph 2. It's
no,
always
no, I'm
0.
looking, I'm still in section 5.4 just
Oh,
for a
really?
second.
Oh, okay, okay, okay.
Yeah, sorry. I know it's a short little section, but I think I got a feeling it's important.
Yeah.
This whole idea of proper time.
Okay, right. I see the sentence you're talking about.
Yeah, so when it says straight lines, hmm,
That was the idea where, like, if you make your space-time diagram,
yeah,
the vert the I should label the axes, x and t. Uh, the vertical line between A and B was the worst one. When we were making those triangles, you save time if you traveled along like 45-degree angles to your
yeah.
point. I think that's basically what they're saying. Gravitational lenses. I assume this book is into that somewhere. If you get far enough in. Maybe in solar system tests of general relativity or something. Um, Okay, so I kind of just glazed past it at the time. We will in this section we'll demonstrate this fact constitutes a variable principle that implies the free particle equation of motion. But in chapter 8, they do the opposite.
And then they said that right at the end of this section too. They said, this is the correct equation of motion for a free particle. And they said it's the one such that du d tau is 0. So the derivative of velocity with respect to proper time is 0. In the absence of forces, they said that's Newton's first law.
Yes. Because just an object at rest tends to stay at rest, object in motion tends to stay in motion. Or like in chapter 3, they presented the same thing in Newtonian context, where the second derivative is equal to 0 for a free particle. Good luck, Ayush.
Okay.
So, yeah. I don't know. Anything else on 5.4?
No, not right now.
Okay. Then light rays. Which I guess not light isn't the only thing that can move at the speed of light, it seems. Which was news. I mean, I guess it wasn't quite news with like forces moving the speed of light. With the quanta of them. They talked a little bit about that in the E&M book. Um, oh yeah, it is weird that U.U depends in different contexts. It's different things. I guess U.U equals -1 is only for time-like world lines.
Yeah.
I wonder if it was space-like, if it'd be +1 or still -1 or something. I hope it's +1. I don't know.
Maybe.
Oh yeah, affine parameters. I kind of understood what they were saying with they could have chosen sigma cubed as a parameter, but it wouldn't have the S queen properties. But if they're making a lot of points about parameterization, that's kind of probably important, but going over my head for now until I see why later on.
Yeah, me too.
Hey Yash, hey funny text.
They said if you have an affine parameter, then any constant times that is also an affine parameter.
Right, yeah. And at least I could follow along with that from the derivative thing. And then energy momentum frequency and the wave vector. We're getting this h bar constant coming into play. And yeah, that's where things are getting really weird. Attack on Titan? No, I don't have any Attack on Titan things. I never watched it. H bar mentioned.
Yeah, is that the first time it came up in the book? Pretty much, I think.
I think so, yeah. Um, I should have reread this
I
before
didn't know
this.
what the K was.
Yeah, that's what I'm trying to figure out again quickly right now. um,
The wave three vector.
V equals P over E. Since the magnitude of V is 1. Oh, I just realized the magnitude of the 3 vector V being 1, and that's basically saying the speed of light. That should be C if C didn't equal 1.
Yeah.
The 3 momentum. Wave mechanics often deal with wave of the form phi of x comma t is equal to cosine xk plus omega t plus phase.
Yeah, I think I've seen waves written that way. Oh, so that K is this K, is it? So X is space, T is time. There's just a phase shift, which, okay, we don't care about the phase shift, but X is space and T is time. And so omega is like per second and K is per meter, isn't it? So K, yeah, I've heard K called like a wave number or something.
Oh, it's just momentum with an h bar factored out. It sounds like that's what FizzBuzz is saying. Anonymous, it'd be cool. I never tried to though. Just made sense, or I was able to at least figure out the math of this at the time, but now it's. Are we getting from 5.67 to 5.68?
Okay, I think I get it. So for 5, 6, 7, you were taking like magnitude of both sides. Is that what we're doing?
Right,
Or
that's a scalar equation. We would need to.
okay, so yeah, so maybe 5, 6, 8, we're taking like magnitude of both sides. And that would give us 5, 6, 7. Yeah, I think
Yeah.
5, 6, 7 is the magnitude of 5, 6, 8.
Okay.
And the momentum vector and the wave vector just point the same way.
Yeah.
Okay, yeah, so FizzBuzz is saying we're just kind of scaling the momentum to change it into K.
In a minute, I'm starting on a master's in the fall. Uh,
And then we got the same deal here. P dot P is 0. Well, I guess if it has no mass, that makes sense.
I'm interpreting that. Ooh. But it, wait, do they, is the momentum, if it, I was thinking that more as a consequence of u dot u being 0. They never
Right.
mention mass anywhere above here. Besides, the header says 0 mass, I guess. Hey, Aaron.
Yeah, I think you're right.
So I I wonder if P equals h bar k is the definition of momentum for something with no mass, but I don't know if k has a momentum hidden inside of it. I guess it's more about the frequency. But I'm not quite sure about that.
How would we prove it? Can we use the definition of the scalar product to prove this somehow?
Because this is a momentum 4 vector. They're not talking about momentum as a 3 vector above. So I don't. Actually, no, I'm sorry. They do give momentum as a 4 vector. Uh, I wonder if the 3 vector components of momentum come out to be 0 for the reason you say. With there's no mass. But that would mean no, that can't be true. Compensating. Oh right. Oh duh. Okay. I remember realizing
Oh,
this. Yeah.
oh crap. So is it, and then there's a negative sign? Is that what happens?
Yeah, the first component has the negative.
Oh, okay. Yeah, okay.
Here we go.
All right. Thank you, Fizzbuzz.
Yeah, thank you.
I mean, they just said that like 5 lines ago, but you know, helps to be reminded.
Yeah. Okay, then I'm going down to the Doppler shift part, which they seem to just kind of pull these equations out of nowhere for converting frequency, or for like converting frequency between inertial frames. But I can believe it. Um, Maybe there's some justification with omega being the time component for momentum, and it looks like the equation for time momentum, I think, or for time. Yeah, that's where I just kind of started. I could follow along the individual math steps, but I the concepts are a little bit lost on me.
Yeah, these last 5 pages I have not read carefully.
Hey, Cook.
I think this is about where I started skimming.
Yeah,
Hey, Dr. Cook.
I did have to look up which end of the spectrum blue and red are on for light. Because at first I had it
Okay.
backwards. I thought blue was the longer one, but I think it's the shorter one. So I was confused by what they were saying at first.
Infrared. Ultraviolet. Wait a second. Yeah, ultraviolet are the ones that burn you, right? So they're the ones with the more energy.
Oh, that makes sense. Yeah.
So what does that mean? More energy, that means they got a higher frequency and shorter wavelength, I think.
I think so. Um, oh yeah, once they started measuring angles in different inertial frames, I got really like it got hard for me to visualize that.
Is that this picture on the next page?
5.9. I think it's related to that. Yeah. Which it's kind of crazy that this happens.
So it's a light source, right? Is that what it is? It's a
Yeah, it's
light
like a star
source.
or something, or some type of radiation. I guess it doesn't have to be light or light that we can see.
Okay. And if it's and if it moves right, the intensity of radiation is increasingly concentrated along the direction of motion.
So if it's moving to the right, the light or an observer would see it as the light being beamed forward like a flashlight in the direction it's moving. I mean, it's still emitting some light the opposite way, I guess, but yeah. So I trying to figure out what the cosine like equation 5.75 with like the alpha prime and what that actually means. Kind of, I didn't get it.
You know what 5.75 looks like? It looks like it looks kind of like the sum of the tangent sum formula, doesn't it? Like tangent of a plus b,
Oh, a little
except
bit.
one of them changed into a constant velocity.
Yeah,
Maybe not, because there's a sign mistake too, isn't there? There should be a negative there somewhere.
yeah. I think it's more of a coincidence, but it's kind
Yeah.
of interesting. Hey, better. Okay, box 5.1. I didn't even slightly get that. I just stopped reading it halfway through. It was so out there with things that I've never learned. Yeah.
I didn't read it, but they said we don't really need to read what's in the boxes to keep the thread. So
So if I would have, okay, so they only barely touched on relativistic beaming them, as opposed to saying relative to like how much they would normally cover it. Um, then I think 5.6 was a little bit lighter, at least. Um, we derive very concisely with four vectors. Run a very long-winded way by thinking about telescopes, what angle the telescope needs to point. Oh, there's a problem about thinking about the angles of telescope pointing. I didn't choose it because it seemed super weird, but there's
I
definitely
read
a
about
problem with
that
it.
in a different book this week. It's
Oh, funny.
called Aberration of Light.
Ooh, that's a cool name, at least.
Yeah, they said if you're looking at a star through a telescope, depending on the time of year, you'd have to like tilt the telescope a little bit to keep it in your view. And I guess they said because the Earth's if it's a star like directly up from the plane that the Earth orbits in, so you're basically pointing the telescope, up from the direction it's moving at right angles to the direction the Earth's moving.
Mm-hmm.
Then the time it takes the light from the star to come down through the telescope itself, the telescope moves a little bit, right? Which kind of makes sense.
Oh, wow.
Yeah. It's what it also has to do? It has to do with that Michelson-Morley experiment where they were trying to detect the ether or whatever.
Yeah. Okay.
And so they were trying to compare like the speed of the Earth with the speed of light and see if they could find the inertial frame that light behaves nicely in.
Hey, Pedro.
But yeah, I guess it makes
Um,
sense if you got a kind of a long telescope. I mean, the amount of time it's going to take the light to get from the top of the telescope to the lens at the bottom or something is nothing, right? But think about in that nothing time, the Earth still moves appreciably, I guess. So
where do I going at an angle would fix that then?
it's not a big angle. It's not a big angle. I think they said the difference in 6 months. If you do it in summer and you do it in winter, or summer versus winter, they said it's like less than 1 minute of arc or something. Like
Oh,
I don't know. It's like 10 to the minus 4 radians, I think is what it was. 10 to
wow.
the minus 4 radians is the difference in angle.
Ghostbusters is agreeing. You can also think of it in the telescope screen that the telescope is not moving at all. Hmm. Um, yeah, scrolling through, it felt a little bit weird how much they're hammering the point of like the orthogonal basis vectors in the lab of the scientist. I assume there's a good reason for it, but I feel like they weren't saying that much for at least parts of this. Um, the time
And they
component.
said
Oh, what?
they're gonna put little hats on the vectors if they're orthonormal. If it's an orthonormal basis.
Yeah. Um, and E zero hat being equal to the velocity is very weird. But I think that kind of has to be the case.
I guess 0 is the time component.
Pedro, I'm just a tutor, I'm not a teacher. Um,
Yeah, well, I didn't read these last few pages, so I don't know exactly what they were talking about here.
they're just giving an example of finding an orthonormal basis with that caution cinch world line example from before.
Oh,
Um, oh god, yeah, some of the stuff at the end here was weird. energy is equal to minus p dot u as 4 vectors. Oh, in example 5.8, they gave a weird thing where um, they calculate the energy of a stationary particle as measured by an observer, but the observer is moving and the particle is staying still. So there's, I guess we're in the particle's inertial frame, and that part was kind of weird to me.
Okay. Yeah, you remember them doing that in Purcell and Morin? They sort of broke it down into 4 cases. It was like, is the charge fixed or moving, and is the observer fixed or moving? And
Yeah,
looking at the fields and stuff. And yeah, I remember they did a bunch of that stuff.
that's how they found, or that's how they like, arrived to magnetism, I think, by looking at a current in different inertial frames.
Yeah.
Um, and there's another frequency example that I only sort of got. But all right, do you want to try getting some actual problems, or do you have anything else in the chapter?
What's this W star?
W star. I remember that being weird.
Oh wait, it says
The frequency in the
light
rest
emitted
frame of
at
the
a
star.
single.
Yeah.
Yeah, okay. Yeah, let's try something.
Okay. Um, Start off with number one, which I think doesn't have an S, but it seemed pretty straightforward at least. Oh, it does have an S. Okay.
Yeah, this looks doable.
Yeah. um, Consider two 4 vectors A and B whose components are given by these. Is A and B time-like, space-like, or null? Um, so we might want to check like A dot A and B dot B.
Yeah, that's the way, isn't it?
Yeah, that feels like the way. So A dot A will be negative minus 2 squared plus a couple of zeros plus 1 squared. So we end up with a negative 3. Oh, wait, now I don't know what this means. Um,
The length of a 4 vector.
we need like.
Oh,
Hmm. It has to do with the angle of this vector. Like 45 degrees is the
we might,
important bit.
yeah. We could draw a picture of it, couldn't we?
I guess so, yeah.
If this was like X and T, if I started here, I'd go down 2 and, well,
I guess
let's not make it
Z.
X,
Yeah.
let's make it Z, right? Yeah. So I'll go down 2 and write 1, so it's kind of like that, isn't it?
I
Hey,
hope
why
so.
did I write a
Yeah, this
Y?
should be okay in space-time land, I think.
I wanted to put a T here, I think. So if this is, so this is 2, right? And this is 1. So isn't that time-like? It looks time-like now because it looks like it would be inside a light cone. Uh,
Um, yeah, it's moving farther in time than it moves in space in the same interval.
If it's a -2, does that mean it went backwards in time?
Either, I don't
No.
know.
Well, it's time. It doesn't matter. It's time like though, right? It's
I
time
guess
like.
it's A points from one event to another event, I think. So maybe two events are separated by a negative amount of time. I don't know.
Yeah, because that picture they had at the start of the chapter, they had arrows pointing up and down for time like,
Yeah, and so I
and
assume you could
arrows
always flip the
pointing left and right
direction
for.
and it's not so
Yeah.
different. Um, yeah, I think I'm down with saying A is time like. B, I would think, well, what would I think? It's a Pythagorean triple if these were just if it's just normal Euclidean geometry, but oh, is B dot B zero?
I think so.
I don't know if that's important or helpful, but maybe it could be null, I wonder.
Yeah, I would make it null.
Oh yeah, if the vector has zero length, that's null.
Yeah.
Okay. All right, see ya, Aaron. Um, but yeah, I assume to tell between time like and space like we need a different rule than just dotting it with itself. I hope the solution tells us that, or like, I guess you need to compare the length of the time component versus the overall length of the space components. Maybe that's it.
Yeah. Yeah, that sounds good.
Okay. For part B, I think this is regular vector subtraction with nothing. We don't need to include any extra minus signs.
Right. Yeah, I think so. Yeah, because adding vectors and scaling vectors was just normal, wasn't it?
I think
It was only
so.
when the dot products came in we had to keep track of the negatives.
Yeah. Uh, minus 15, minus 19. I don't like these numbers, but that's what we get. Then A dot B. Oops. Um, so it's -2 times 5, but with a negative out front. Plus 0, plus 0, plus 4. So we get a positive 10 plus 4 is 14. Really? I thought they said somewhere, oh, it's maybe a problem we have to do. Maybe it's, I might have skipped that problem. But I thought these, okay, yeah, I skipped over it. But number 2 says that there's a similar formula for A dot B equaling magnitude of A, magnitude of B, cosine theta, but theta isn't, sorry, cosh theta. I'm saying this wrong, but as four vectors, A dot B equals minus AB cosh theta, where theta is a hyperbolic angle. But we
Okay.
found that B is magnitude 0. So why didn't we get 0 here? I didn't square 4, did I? No, I don't have to square 4. What? I don't know.
Oh, uh, okay. It says in that question that it only holds for time-like four vectors.
Oh,
Maybe that's
okay, great. You're right. Okay. Maybe let's check the answer on this then.
okay.
Okay. Uh, 5. So they do calculate the magnitudes. A is time like, B is null. So what is space like? Oh, a space like should have positive magnitude.
Okay.
That feels like it makes sense. And that's another way of saying what we were saying before, comparing the space and time component.
Yeah, yeah, that's what you said. Yep.
Okay. We got B correct. And then C is 14. Okay. Looks like we did it right.
Okay.
All right. Well, no matter how else the rest of these questions go, we at least got this one right.
Yeah.
Okay, the next one I had was number 3. Because number 2 seemed nice, but there's so many other interesting questions that I figured that one would just be a bonus one for another time.
Yeah, maybe I'll think about number 2 later. Maybe.
Yeah.
Because I was thinking more about these hyperbolic cosines this week.
Yeah, like they're so weird.
Yeah.
Okay, so number 3 is another straightforward. Free particles move along the axis of an inertial frame with speed v, passing through the origin at t equals 0. Express the particle's world line parametrically in terms of v using proper time t as a parameter.
Hmm.
Um, so I assume they're asking for a 4 vector x.
Moving along the x-axis with speed v and passing through the origin at time equals 0.
How do you feel
Well,
about
that
this?
seems pretty fair. Express the world line. Proper time tau. So we have to find, so let's see. Oh, you already did it. Oh, wow. Okay. Okay.
That's at least what's coming to mind. I'm just
No. Yeah. So so let me see. There's formulas, right? Is that what you used? You use those Lorentz formulas or whatever?
uh no, this just kind of feels right to me, I guess. The,
So proper time
hmm.
tau. So time is tau, and then v times tau. Oh, and it's not moving in the x or y directions.
I, I assume this is okay. Like whatever we can make the time component anything we want, as long as the space component is v times that. I hope so. I hope I'm not missing anything with just the thing I'm worried about is whether tau is our time component or if it's more complicated.
Hmm.
I think it's okay though.
What about so on page 80, right? They had the Lorentz boost of a vector. And
Um,
yeah, equation 5.9. Section
I see it.
5.1, I think.
Yeah, 5.9.
And I'm wondering if those look like they would, uh, if those might apply. They might.
Oh, Cook, the time component is proper time only in its own frame, in the particles frame. So yeah, maybe we do need these.
Yeah, because that gamma shows up, right? I wonder if we need a gamma anywhere.
I, yeah, because we would be measuring time differently than the particle. Yeah, that makes sense. If we were in the particles frame, that would be that's when the proper time would be the time component and nothing else. Oh, Cook is saying to make it equal to CT VT and calculate t in terms of tau and substitute. Oh wait, I assume C is gamma. Oh, this was they did this as an example, didn't they? Going from sigma to tau. We were talking about this one. See, speed of light? Really? Why would that be there? Let's get rid of that. Get rid of that.
I'm just writing down these transformations here.
Oh, okay.
I don't know if we need these last two. We don't need the last two.
It should be the same in each frame, yeah. Um, nope, I'm doing this wrong. I'm trying to follow the books with the book example for uh doing this parameterization thing. Wait.
So in its own
Ugh.
frame, it's a free particle. It's a free particle, so we see it moving with speed v, right? Is that what it is?
Yeah,
When we were in a
that's the
fixed
speed we
frame,
measure.
we see
Yeah.
it moving with speed v. Passes through the origin at t equals 0.
Wait, so Dr. Cook, you're saying that c is speed of light. At least in chapter 5, we have switched to c equals 1. I hope I could safely just delete the c's, or, make them all ones and put it in the book's terms. But I think it's just going to end up getting the Lorentz equations that you've written down. Maybe. Uh,
So the particle's world line is
plus some constant c, but that's equal to
this
0.
is this one.
You can if you wish. Okay. But this just ends up being gamma times tau. Okay, so
That feels good.
um, that means time component is gamma tau, the x component is v gamma tau, or maybe gamma tau v. Would the Lorentz boost have gotten us there directly? Uh, Something we need to zero out here for this to work, right?
So basically you had to change each t into gamma tau, right?
Uh, right. And t is just a generic parameter, as I understand it.
Yeah.
Maybe that's a poor choice of letter when they say t equals 0 there, but or maybe not. Maybe it is the same t. I think I've gotten the right answer. I feel a little bit shaky on why, but
They had an example in the book that was like this. And they were talking about where was it? I read it this morning. I don't know where it went. Maybe it was it was 5.2. Lorentz boosts preserve the orthogonality of coordinate axes.
oh, I might have figured out how to make the Lorentz boost equations work.
Yeah, we were talking about that a little bit ago. Arc length parameterization.
Yeah. I think for the Lorentz boost that you wrote, these x's are in the particle's rest frame, so those are just always 0. And
Well, there you
the t
go.
would be tau, because that's the particle's proper time. I think
And
that's how we would
I
use
might want
those.
to, and I might want pluses instead of minuses, right?
Yeah, there would
I
be a
think
sign
what,
issue, but I think it'd be the same.
yeah, because they said you could just like change the sign of velocity and you're basically reversing the way the frames, you're reversing which one's the observer and which one's the one being observed or something if you just change the sign of V.
Yeah, I guess the 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 particle would see the other frame moving away the speed minus v, so we could flip some maybe that v would get its sign flipped, or both the v's would get their signs flipped. Okay. I'm gonna check the answer on this one too. Try parameterizing an xy line with slope v by its own length. Might be elucidating. Ooh. So if we define a line parametrically with, say, t and 2t, and we want to parameterize it by length.
Yeah, okay. So
Uh,
radical 5, right?
5 or 3? Oh yeah, 5.
1 to 2 to, yeah, I remember this. And then you got to solve for t, don't you? So t is s over radical 5.
Yeah. So we've just normalized it, it seems like.
Yeah, because if s is 0, we start at distance 0. Yeah, s is like your displacement or something, isn't it? So if s is 1, you've moved 1 unit along the curve now.
Oh,
Yeah, that seems right.
I guess so, yeah.
Yeah, it's kind of like, oops, what am I doing? Coming along here. So this is like 0, 1, 2, 3. It's kind of like you had a ruler and you just tilted the ruler up so it's going along that line.
Oh, and these would be like the inches or whatever.
Yeah, yeah, inches or whatever, yeah.
Hmm.
So when s equals 1, we'd actually be at like 1 over root 5, 2 over root 5.
Oh, right, yeah, we could work that with triangles. I guess that's what we did without saying it. And so this is basically the same math that we did, just different parameterization goal. Well, no, proper time is the length, just in space-time.
I wasn't watching. Did you check the answer? Was it right?
No. I can do it now, though. Now the answer to 2 is long. Okay,
Gamma tau, yeah, we just used gamma instead of 1 over root 1 minus v squared, but it's the same thing.
yeah.
I think it's the same thing, right? I was thinking of that as 1 over root 1 minus v squared.
Yeah. It's the same thing. They didn't say how to actually get that. They just said what the answer is, which is a little annoying. Okay. Um, Next up, I got number 4. Oh yeah, okay. We're no longer in S land. All the components of the 4 acceleration vector A is defined as du d tau in terms of the 3 velocity v in the 3 acceleration A equals dv dt to obtain an expression analogous to 5.28. I didn't grab that. I don't know why I didn't. Um,
Oh, this is what you were talking about. A dot U equals 0.
yeah,
Oh no, that was F dot U we were talking about.
but A or F is as ma, so it's the same thing.
Okay.
Okay, so where would we even start? Well, don't we just take 5.28 and take the derivative with tau?
Yeah, I guess so.
They were doing some tricky chain rule stuff. You're saying the time component, trying to. I'm hearing what they're doing with velocity for acceleration. 5.28, no, this is velocity. They want us to get this for acceleration. Oh, the previous? Uh, it basically is, but we need a tau involved. Yeah. Integrate 5.28 with respect to tau gives the answer to the previous exercise. Okay. They're doing stuff like this to find the velocity from the position.
Yeah.
That game is a constant, though. Or is it? The accelerating, I guess it might not be a constant. Well, it's not a constant. Okay. Um, what are so if this is right, which just said it might not be right in the first place, but the time derivative of 1 over root 1 minus 3 vector v squared times something. Hey, Aziz. And then what is my dt d tau that I wrote?
I think dt d tau is gamma.
Um, yeah, I think it is. Okay. And so velocity is a function of t, I guess. I'm sorry, Aziz. What's happening with this derivative?
Yeah, I remember being confused at one point in this chapter. I can't find where it was now, but there was one point where I wasn't sure if v was supposed to be constant or not. I don't remember where it was.
I wouldn't know. I guess it's not. It's often a constant, but doesn't have to be, I guess, in the context we were talking about it. Okay, so this might be not terrible because this dv/dt is 3 vector a. So it's v. Oh, I guess dot. Uh, yeah, those are both vectors, so we can't just multiply them simply. And then that's a square. Like that's gamma squared, right?
Hmm.
Or gamma fourth. That's kind of crazy. The time component. I guess. I guess we can go to a space component for acceleration. Just take the
Okay.
x. Then these should all be the same once we know one. Uh, doing this wrong. So that's um, I guess Vx. Are they doing superscript? I'm getting confused with whether they're doing superscripts. Okay, they're doing superscripts for this V. Ugh. Um. Oh wait, would this be Vx in the denominator? No, it's still the overall. Okay. I guess yeah, that's gamma. Okay. So that's the time derivative of that thing. Which I guess is a quotient rule. Okay, well that's annoying. Hopefully this cleans up. Okay. Low D high. Um, that's going to be the A component of the 3 acceleration minus high D low. Twos are going to cancel. Wait, up above. Is this the this is the magnitude of E. This isn't a dot product. Or these are both magnitudes, aren't? I'm just realizing in the definition of gamma, they're saying 3 vector V. I think it made the magnitude of 3 vector V. Um, I guess they would have gone over this in chapter 4. Just because as they brighten, it doesn't quite make sense to me what that V is.
It's a 3 velocity.
It is. Or like I know that. I feel like in the context they're using it though, I don't know what they. One minus a scalar one minus a 3 vector doesn't make sense to me though. That's what I just realized.
Yeah.
I guess what are there different factors of gamma for each direction? I guess you would need that. Like maybe you only take the relevant direction. Because couldn't you have different like length contractions? If you're moving in like
Yeah.
the XY direction, you'd be contract by different amounts in the X and Y directions. I feel like you could. But then what is this for time? God, okay. Ugh. Does time take the overall velocity? Why would they use v with an arrow if they mean the magnitude of v?
Well, okay. It could be, is it? No, it can't be, can it? Because it's the time component. I was going to say maybe this is three equations in one, but it's not. It's one equation.
Yeah.
I think you're right. It must just be the magnitude.
Okay. So I should. That's that's not a dot product there.
It must just mean, it means v dotted with v, doesn't it? And as a three vector, it means like the dot product of v with itself,
I guess so.
I think.
Um, then what will my is my a also a magnitude? That's the next question. It must be because this should be one dimensional. Or like just the time component should only have the one dimension. Okay. So then coming over to X land, I think everything should be Bx. That means it's not gonna be like a universal. It's not gonna be the same gamma, and it is the same gamma in 5.28. They're saying this comes from equation 4.22. Let me look at where they originally, or let me look at 4.22 then. Okay, I really hate they're doing things in one dimension now. So they introduced gamma, things were only moving along the x-axis, but when we're doing this in general, we can't assume that. I assume we're not going to assume that. So do
Let's
we?
assume it for now.
Uh. Okay. Ugh.
Maybe let's see. Maybe what we have to do is instead of doing it one component at a time, do all three at once. So think of it as like Vx plus.
Maybe. But I might just keep grinding out this quotient rule in the meantime.
Yeah.
Uh. I need a minus sign because it's minus. Wait, yeah. Yeah, I need a minus sign, so that becomes plus.
Can I put the X's back? Wait a second, let me think.
Sure.
What if you, let me just try something here. What about this A here? So
I don't
this
know.
A, shouldn't this be, this is like AX, isn't it? This would be a
Uh,
component of A.
yeah, that should be it.
So maybe we're okay then.
This, yeah, we can split into two fractions and get something that could be reasonable.
Yeah,
Gamma
because
to the
that was the
fourth.
X component. So if we do all three components, then maybe we can kind of factor out the
Oh wait, this doesn't
velocity one.
cancel like that.
Yeah, I think we're in business.
Um, I'm trying to think of this separate way to write this. 1 plus b gamma squared to the
Wait,
fourth
maybe there is.
vx. Yeah, that doesn't look that clean to
Oh,
me.
there is a squared missing there, isn't there?
Oh wait, maybe I just dropped that squared. Oh, I dropped it. It is supposed to be there. So that does give us the cleaner cancellation. So we get gamma squared ax plus gamma to the fourth vx squared. Wait, yes. And then the other two components would be the same thing with the other components. So how would this look written as 1,4 vector? The time component, gamma to the fourth VA. These are magnitudes, allegedly. Uh, maybe I think we just drop I think they would just drop the arrows for magnitudes. And then the other components, I guess, would be that. I have no clue if this makes any remote amount of sense.
Well, they said something, we had to come up with something similar to equation 528. So,
The units definitely. I don't know if the units are at all. I guess the units for this second component check out. I guess the units check out, yeah, okay. Because gamma is dimensionless, V is dimensionless, A is something. Inverse meters or something weird.
yeah, what are the units?
Yeah, A would be inverse meters. V is dimensionless. Gamma is dimensionless. So I think the units check out. But a lot of things would check out. I'm okay with looking at the answer at this point.
Okay.
All right. This is number 4. Okay. Let's see. I won't scroll all the way down. See what like how the star looks. Oh, that seems promising. That is a dot product. Well, if we're more,
Did you get it?
I think we need to be more careful with dot products. But I think we got the right components in the right spots, in the right gammas.
Why don't they have a capital A there?
I don't know. Oh, and the solution that is the 3 acceleration. The solution just
Okay.
used capital A, I guess. I don't know.
Yeah.
Oh, we never checked the dot product.
Wow, how'd you do that?
AW.
So you basically just use the chain rule, kind of like they did for velocity.
Yeah.
Okay.
So the time component is easy to correct. Just put that dot product back that I thought we had to remove. Where did we go wrong with the space component?
Did we have a mistake? I thought it was right.
No, we're a little bit off. The dot products are needed, but like we have the right gammas in we have things in mostly the right place.
Okay.
Um,
Oh, we're missing an A.
yeah, that's the top thing that we didn't do right. Um,
Oh, wait, is it chain rule? Maybe it's chain rule. Yeah, ddt of a function of v is ddv of the function of v times dv dt. Yeah, there is an A that pops out.
was that
Does
when I
that make
was?
sense?
Was that
I'm
around
saying
here?
right here.
Yeah, we would. I guess we're taking the derivative. Wait, why is this Vx and that's just V?
Yeah, good question. I just figured I'd throw the X up there.
This Vx came from the numerator.
Okay.
I think that V needs to be a not, and that's going to make more sense, I think. That V came from that V, and then we needed the dv dt out here, and that's going to give us an A.
Yeah.
So I guess we're ending up with vx dot v dot a.
Well, that's fine, because then when we sum them, we'll have vx v dot a plus vy v dot a plus vz v dot a. And when
Oh,
we factor it out, it'll become v. Does that sound right? It might work.
yeah. I'm just gonna 1 second. I'm gonna bring the actual answer into the Excalibur. I was wondering why there's no dot here, but this V is our Vx.
Ah,
So I think we're okay.
yeah, that v will be the sum of all the components.
Yeah, so that's where we're getting V dot A from up here. A small a, I guess.
That's pretty nice, Don. You were very close. I mean, you had the 90% of it there.
Yeah, I'm realizing how much I dislike this vector notation. It's really confusing, but We had
Yeah, I think
the
this
right idea.
summation, the summation notation is going to take some getting used to.
Yeah. And then we need to do a dot u. We just never did that piece.
That's true. Yeah, we didn't finish the question.
We are after time though if you want to dip out, but I don't know if we're gonna try and do
No,
that
I got to
quick.
see it. I got to see it through.
Okay.
We're almost done.
So then a dot u minus the a component is gamma to the fourth v dot a times just gamma. Yep. Plus. Can we do this in one go? I think we can. I think if we pull the gammas out front, we get a gamma to the fifth. Oh, wait. Maybe I shouldn't try to be fancy. No, let's just do it the old-fashioned way. I think we're going to be able to turn this into a dot product, but I don't want to jump the gun.
I noticed your microphone's cutting out on Discord a little bit.
Oh no. It's annoying. It's just I have everything on automatic for. Did it only just start happening?
I've noticed it a couple times. It seems like it's happening a little more just recently.
Okay. Let me try doing. I might get some more background noise coming across, but hopefully it'll cut me off less. I might just be moving around too much, to be honest, and like getting too far away from the microphone. But if there's background noise, let me know.
Okay.
Actually, just gamma v for each of the v components. Okay, so then we're going to get y z z. And so we would want to justify. What do you want to justify?
Well, everything's gamma to the fifth, so we can get rid of all that.
Right. I guess we don't know
We
it's
can
equal to 0
factor
yet. I don't want to like factor it, yeah.
Yeah, we can factor the v dot a out of those final three terms.
Can we bring it out of them all?
Yeah, let's bring it out of all of them. Good.
Oh, no, I don't think we're gonna get normalization. Or we're gonna get -1 plus vx squared. Oh, I think this is a normalization thing.
Yeah, maybe.
So I think they said somewhere that, or this is v dot v as a 3 vector, and I think that has to be +1. I feel like they said that somewhere. It's going to have to be in order for this to be 0. Oh wait, no, or was that might have been for null lines.
Oh,
Um,
wait a second now. Yeah, because we want that negative one to be a positive one, don't we? Or do we want that negative one to be a v squared somehow?
yeah. Welcome back, Fizbuzz. We're mostly getting our asses kicked, but
Oh, it's much nicer than I thought it was going to be. I thought we were going to really get killed.
that's true. I did think it'd be
Yeah.
worse. That's a silver lining.
Well, I think so far we've come up against some of the gentler questions, right? I mean, I think the average question at the end of this chapter is going to be harder than what we've been doing so far.
Yeah. Um, we want to justify free vector v dot v being positive one. Why would that be?
Oh, wait, I think I see something. Um, what about this term here? Did you lose this one, or is this gamma squared A was inside this as well?
Oh, oh my god. I'm just dropping stuff. Dropping it like it's hot. Okay. Gamma squared, is this going to be the... This should be the x component of A.
Oh, okay.
So that, okay. So we need to update a bunch of this stuff. Ah. Okay. So we can't quite factor out the gammas like we were hoping.
Hmm.
I think I'm seeing a v dot a though, because we're gonna get, let's be gamma cubed, but we're gonna have a vx times ax plus vy ay plus vz az.
Hmm.
So I'm gonna make that plus gamma cubed. I guess that's a dot v, but isn't it, if you reverse the dot product, I think it doesn't matter. So I'm going to write it as v dot a then, just to make it the same order as the other one. And then what do we get for the other components? We get gamma to the fifth.
Yeah, something's gonna happen here.
V dot a times v dot v. think that we can write it like that.
Yeah, because v squared minus 1 is gamma, isn't it? Let me think. No, gamma squared. Gamma squared. Yeah, there's something going on here. The first and third terms. We can factor out a 1 minus v squared, and that is gamma squared times 1 minus v squared is 1, I think. Does that sound right? Gamma squared times 1 minus, oh, I'm not writing a pen. Gamma squared times 1 minus v squared equals 1.
Oh, yeah.
That's going to help us, I think.
Um,
Yeah, I think I see it. Because I want to say these two terms, this one and this one, put them together and factor out and use this result. Yeah, is it going to work? Maybe.
I could. We could use that cancellation for these first two terms. They would be gamma cubed v dot a. I don't see how to use it for the
No,
first
leave
and
it, leave
third.
that one. Let me,
Yeah,
if I take the first
go
and
ahead.
third ones, let's take this and this, put these together. So I get gamma to the fifth, v dot a
Hey, Everton's best. Welcome in.
times v squared. I want to say this is v squared minus 1. See that? I'm going to say
Yeah.
1 minus, I'm going to put a negative over here. Is that true? Sorry about the handwriting. So here I'm saying v dot v is v squared, this v squared here. That's true, right? V dot v.
I buy it. Yeah.
So then I can say this, so I can factor out a gamma squared out of here to go with the 1 minus v squared to make a 1. Let me just write
Oh,
it.
nice. Okay.
Yeah,
Wow.
yeah, yeah.
That's a good
I gotta,
spot.
I gotta practice writing on here more. Usually my handwriting's not too bad. This is kind of atrocious, but anyway, you can see what I mean.
Excalibur doesn't make it easy.
So this is equal to 1. Well, that would, yeah, we're done, right? We're good.
Yeah. This is 0.
I
Nice.
think those steps are I think those steps are legit.
Yeah, we can see what the solution says, but that looks right to me. Oh, well, okay. They don't say. It just says then one can check it explicitly, and they don't actually
How?
say how.
They
Okay,
don't
well,
say how.
for what it's worth, I believe this, so that's good enough for me at least.
Yeah, well, I never would have come up with the first part of it where you had all those gamma to the fourth. So I honestly, I didn't have faith. And then you got checked the answer, it was right. It was like, man, why didn't I believe him?
Now, I didn't believe it either. I was like, gamma to the fourth is so weird. I
Nice
still
work.
feel super confused about like their notation now, but we got there in the end. But yeah.
Yeah, I'm gonna have to read this whole chapter again. I actually read the first half of the chapter twice.
I did too.
And then the second half, I didn't really quite get through all of it. I do that a lot. Like if I'm stuck, I just got to go back and start over. I figure it makes more sense the second time.
Yeah, I mean, it really builds on itself.
Yeah, I was trying to read this other book that Physics and Depression mentioned on special relativity. It's like, it's a whole textbook just on special relativity.
Oh wow, that could be fun.
Yeah, I couldn't find a PDF of it, but it was on Internet Archive, so it's on there.
This was asking which
Oh,
book it is.
FizzBuzz. It's by an instructor. It's by an author named Helliwell. Helliwell, who I think's from Harvey Mudd College. And let me. Oh, come on.
And yeah, ever since we're just studying this for the first time, so we don't quite understand it for ourselves. LOL.
Yeah, Helliwell.
Hmm.
Yeah, I guess Physics and Depression said he knows the guy, so that's cool.
Oh wow.
It seems very nice. I read the first like 3 chapters. The chapters are only like 10 pages or something, but it's very gentle.
Oh, that's good.
It had an interesting question in it. It said, if you're in a spaceship out in space, deep space, and you look out all the windows, you got this all windows in every direction, and you can see a uniform distribution of starlight coming at you from every direction, right?
Okay.
And then they say you speed up, you accelerate your spaceship, so you're moving very fast now in one direction. And they want to know when you look out the window, where do you see the stars now? So before you hit the gas, when you're just at rest with respect to all the distant frame of all the stars, you see uniform starlight in every direction. And then after you've sped up to some high, some fraction of the speed of light or something, they want to know what happens to all the stars. Like when you look out the window, where do you see the starlight? Has it shifted, in other words?
Uh, I think with relative, this is probably relativistic beaming, and I think it's gonna be
Yeah,
like,
you know what?
oh, I think it's gonna be
Uh,
that's how it looks like Star Trek with the warp speed, where they start to like move away from you, like they move like behind you.
I'll bet you it is relativistic beaming because it reminds me of that picture in the book where they show the circle, being accelerated and all the arrows are kind of bending.
Beam me up, Scotty.
But I'll tell you, it was very counterintuitive. The answer is very counterintuitive. I'll post a question in the Discord and you can think about it.
Yeah, sure, sure.
Yeah. And
All
no, I
right.
forget. I had a question I was going to ask you, but I forget what it was.
Oh, uh,
Oh yeah. Oh yeah. Did you watch any more of that video that Dr. Cook posted with the
shoot,
train that turns into?
I forgot.
Oh, that crazy video.
I've been so distracted with other stuff that I keep telling myself I need to. I will do it after the stream.
Oh, Don, I remember what I was going to say.
Mhm.
Uh, there's a new Ghost album came out this week. I
Oh,
think it came
really?
out this week. Yeah, a brand new Ghost album. Oh, it's fantastic. Actually, I'm really enjoying it.
Maybe we'll have that in the
Yeah, I'm kind of
background.
I'm kind of hooked on it right now.
Okay. Skeleton?
Yeah.
Okay.
Yep.
Yeah, I'll probably play it.
Yeah.
Um,
Some cool songs on there. But I should let you
all
go.
right. Yeah, thanks for being here. We might be able to just do
Yes.
this for one more week. It depends how successful we are next weekend, I guess.
Yeah. You know what I was wondering is how much do you think the rest of the book is going to depend on this chapter here?
I'm kind of hoping we can just slide along in the
Yeah.
future chapters.
Yeah. Same here. Same here.
Like, we can just take the end results as facts when we need them and not need to understand it too deeply.
Yeah. Yeah. That's what I think too. The first stage of learning is being able to like blindly apply formulas, You do that first, and then later you hope that you'll have some understanding of what it meant.
Yeah, I mean, that's kind
Yeah.
of just how I learn normally, like just blindly use it and it sinks in eventually.
Yeah.
Variational principle is very important, Cook says. All right.
Yeah, I had a feeling it was, yeah. Because they were talking about, you and Dr. Cook, you were telling us about proper time, and I have a feeling proper time is really a key idea.
Yeah,
And they did say it, they said it's going to come back in chapter 8.
I still have a hard time thinking about proper time when it comes to like the space-time diagrams. It is just the length of the path, but like I don't know. It's just weird.
The other book, I was just about to say it, wristwatch time. Yeah, exactly. That's what Helliwell said as well. The phrase wristwatch time. Yeah.
Oh yeah.
Because when I read that in the Helliwell book, I was like, I think that's what Cook said, wristwatch time. Yeah.
All right.
All right. Yep.
Well,
Well, have a good week. We'll see you next time.
you too.
Okay.
Bye.
Yep. Thanks. Thanks, Don. Bye.
All right. Let me start playing that Ghost album. All right, I'm gonna need a minute to switch things over. All right, Poison Mouse, sleep well. Thanks for being here. Twitch info is updated. Let me update the YouTube info. It's like chanting right now. Hey, Lucas. Oh, here it goes. No, I'm not gonna stream for like a bunch longer because of my voice, but I'm gonna stream for a little bit more. Oops, I didn't actually post the notes. Okay. Oh yeah, that text down there isn't quite accurate. Switching subjects, I guess. Okay. I'm just switching over like my Twitch and YouTube info. 70%. Oh, nice. That's within the range that you needed, right? Um, you're around 68. Okay, there you go. Hey, Arslan. Okay. A friend did ask for me to think about a problem. Uh, and I want to at least spend a little bit of time thinking about it. Um, Let me see if I can summarize what the question was. Um, I'm from America, Arson. In a gambling game, you always lose until the final round. Your goal is to wait. This isn't the right way of phrasing it. He's asking about like bets to recover your money in the sequence of percentages that you need to bet. Let me get the exact thing that he said. Oh my god. So many things been. There we go. This is. I want to condense this down, but this is the message that he wrote. Welcome back, Everton's. Arsene, if you have a question, feel free to let me know. Um, how much to? It's like that's what he said, and I'm trying to like rephrase it in a way that's more directly related to the math of what we want to do here. Hey, Mary, how's it going? Boom, 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 boom. So if you, this is some really like messy scratch work, but basically if you, ugh, yeah, color code. This is an album just dropped by the band Ghost that Fembox likes and just told me that they released this. So I've only listened to a couple of their songs to be honest. Arslan, I don't want to talk about that. So if you bet 25% of your money and you lose, you now have 75% of your um, money remaining. If you want to get back to 100%, uh, you now have 75% of your original amount. So you would need to bet 33% of the amount you currently have if you want to get back to your original amount of points. MIT? I don't know, Arsene. You do have to just look on their website. And then if you lost that, you would be at 50% of your points, of your original points, and you'd have to go all in. And then at that point, you win or lose, and there's no going back. So even when you think about it as in terms of an original bet, rather than number of rounds, if you start off with a 20% bet, you now have 80%, and you'd have to bet a quarter to get back to 100. And then if you lose that, you'd be at 60 and need to bet 40. No, it needs to be more than half. Why can't I do math? It's 100 minus 60 over 60, right? 40 over 60. So 2/3. Does that make sense? Sixty times 3 over 2. No, that doesn't make sense. What am I doing wrong? The distinct improbabilities. This is I'm just a tutor, Arsene. Um, I don't know why he was thinking about it, but he was just thinking about the sequence of bets that happens if you have $100 and you bet 25% or $25, in the example that he gave, and you lose, you just have $75 left. If you want to get back to your original $100, you would then need to bet 33% of your current amount, because that's $25. And if you lose that, you're down to $50 and you have to go all in. And he's asking about this kind of sequence of percentages. Like, how can we calculate it for an arbitrary bet, I guess? And so I'm trying to work out for a few cases and just seeing if I can spot the pattern. Arslan, I don't think that I can. Hey, Aaron. You should get some sleep. 25%, which is leaves us with 60. Then we would need to bet 2/3. Okay, yeah, I see why now. It's two-thirds now. Then if we lose that, we're down to 20%. And I guess this is a weird thing where oh, Bombacks, hey. No worries if you just want to sleep. Don't let me keep you up. But I was originally trying to think of this problem in terms of the number of rounds, but I think it's probably easier to think about it in terms of the starting bet amount and just working out what happened from there. But if you start with like a 20%, I'm getting to a weird situation where we're left with 20% of original pot and we can't get back to the original in one step. It's like we could just go all in and then no worries. Okay. Um yeah, once we fall below the 50% of it fall below like the 50 like dollar mark where we can't get back in one step, I assume we stop because then things start getting weird. But yeah, so I guess there should be a way of thinking like um if our original bet percent is P, then the sequence of bets, like we should be able to work this out. Yeah, it I was talking about even defining what else we want to track here, but I guess we want a formula for that sequence of bets. Um, so the first bet is just P. The next bet is 100. I guess 100% minus P divided by P, I think. Um, so what would that, in like this case, 100 minus 20 is 80. P, I'm just saying is the bet that you're like the percent that you're betting at the very start. So it's like this 25% uh in the example that you said. Yeah. And this is the formula for like a percentage change, but I'm trying to figure out if this is actually right. 100 minus 25, oops, over 25. That's giving me 3. That's not right. Do I need to flip this to be a third? What if I did 100 minus 20 over 20? That's 4. So I do need to flip this for whatever reason. P over 100% minus P. Not equals. And the next one, we would do the same thing, but with this old number. Or but with like whatever number came last. Hmm. Yeah, P1. So I guess I can figure this out recursively. But I don't want it to be recursive. Um, Oh, wait, I should check the second step, I guess. Proves an exercise for the reader. No. Yeah, percentages are weird. Um, wait, why isn't... what is this? Why isn't... Maybe that's when we're supposed to... That's when we're supposed to stop. I shouldn't be checking the formula with that. I should be checking, I guess, with this one if I want to check an extra step. The formula wouldn't be valid for the thing I was trying to check it for. But no, that's a problem. If my formula is right, which is evidently not, when I plug in 25, I should be getting 2/3, but I'm not. So oh, I do that a lot, to be fair, but this feels harder than it should be. Like, I feel like there should be some simple thing, but it's just hard to see. So does it... Mm, it needs to depend on the amount that we still have in some way. It's in your mind, but it's not. Yeah. So I maybe need to do like 100 minus P1 in some way to get the amount remaining in round two. Or I guess the amount remaining after round one. But then what am I doing with that number? I'm figuring out what percent of that we need to bet to get back to 100. This can't be right. That's the same thing I said before, basically, but even more wrong. We... God damn it. I feel like we should be able to calculate this purely just depending only on these percents. But we need to express the percent of original in terms of these percents, and that's where I'm getting tripped up. Watch. Oh, I mean, I haven't said anything that's that helpful yet. And I might not be able to. I don't know. Percentages are kind of cursed. The quadratic formula? Yeah, sure, Papadoria. Um, okay, we're trying to figure out 80%. Eighty times one plus what equals 100. That's what we're trying to figure out. It's hard to read on your phone. Oh, true. Yeah. You're not the most sober person. Yeah. Sometimes that helps, but usually it hurts. Um, that's the thing that we wanted to solve for P. P is 1/4. Okay. You'll be indeed, yeah. Okay, and so this 80 came from 100 minus the previous bet. Okay, so it's going to be 100 minus P1 times 1 plus P2 is 100. All right, see you, Bumbex. Sleep well. So P2 is 100 over 100 minus P1 minus 1. Would this work to get us that 25? 100 over 80 is 5/4. Okay, yes. Oh my gosh, okay. This feels like something. Over 100 minus P1 minus 1. Now, does this pattern repeat for any P's going on? I think this 100 might need to change. Or does it? It's going to be 100. It does. Or like, this term is whatever our remaining wallet has, or whatever our remaining points are. That's why this thing is so weird. Hmm. Okay, so the real question is just to see if we can come up with some way to track our remaining pot. But since Bobax went to bed anyway, let me think about Papadoria's question. Then I'll come back to that one. Okay, so you're thinking about root 5 minus x equals 5 minus x squared. Wait, if you square both sides, oh well, no, not necessarily. Okay. Relativity and Papadoria in the same afternoon, true, Fembox. So quadratic in terms of the number 5. Oh. So yeah, so you're saying that if you square each side, 5 minus x equals 5 minus x squared squared. You could think about it minus x squared. So it's not quite a quadratic. So it um yeah, and so what you did to expand all that, but you're asking about the sneaky way. The thing that makes it's not quite a quadratic. It's not or if we had 5 minus x squared minus 5 minus x equals 0, this is just a quadratic, and you could do like u equals 5 minus x and get a lot simpler of an equation. Install that for u and then plug it back in. Um, but the squared here messes that up, if that's what you're saying. If you're trying to do the quadratic formula on this, if it was right, I think that's by luck. Maybe it's not, but what you could do is you could still do the same substitution, but you'd have to do that as a difference of two squares, and it would be simpler, but not as simple. Are you asking about something else? So you want me to actually expand all this, which we can do. Hey, Melinda, this is a question from Papadoria. I'm not seeing what you're saying, Papadoria. 5 squared? I don't see a 5 squared, or at least the 25 went away. Okay, yeah. I'm not quite getting it. Oh, Finbox, you're figuring out the that way? Um, yeah, I'm gonna wait to see what you write out then, because I don't quite know where that's going. If I go back to the percents for a little bit. If I want the next one in the progression here, I would need to do. I need to modify this term to basically get to that 60% in that example. It'd be 100 minus P1 minus the amount we just lost. The amount we just lost is the same amount times the amount we just bet. I guess that's P2. And we want to solve that for P3. That's kind of crappy. Once we factor out a 100 minus P1, okay, let's test this formula, I guess. Wait, what stage would this be? C3? Hey, Anders. So, wait, that's P0, P1, P2. Wait, what? Uh, yeah, we were talking about that down here. Salvador is writing something out because I didn't quite understand what he meant. But that's a question that we were just working on before. Take your time, Papadoria. Like, we know how to solve it, but he's asking a specific way of solving it. But yeah, aside from that, I've been working on, aside from then what you wrote. Oh yeah, it is. I didn't even see that. Yeah, what you wrote would be a lot easier. Oh wait, isn't this still? Can we still divide out the root 5 minus x though? Doesn't the same thing still apply? Like, can we make this two different problems? X equals -5 definitely does not work though. Oh, ha. You're right. That's why it doesn't work. Never mind. Okay. I was like, there's no way that I was getting a wrong solution. I didn't square the 5 when factoring. Was that the thing that I just said that was wrong? Or did I forget another 5? Or did I forget another square? Yeah, okay, okay. Sent it? Okay. Squaring each side. Multiplying it out. What is happening? What? 5 minus x equals 5 squared minus 2 times x squared times 5 plus x to the 4th. Oh my god. You're using... That's what you meant? Uh... So here... Oh my god. Papadori is doing a quadratic equation where 5 is the x. There's like, you know, a 1 there. So you get 5 equals stuff involving x. I think that's allowed. X is just a number. Jassy says sure. Hey, Krim. I've never thought to do this. I could see potentially missing out on solutions if you end up with an x in the denominator. Like if that was 5 squared times x, maybe you might miss out on x equals 0. But I don't see why you couldn't do this. Like, why does this work? Because it's just all numbers. X is just a number. It's not a special one. Like if you were to write out this is a number squared plus 2 times a number plus 1 equals 0. I guess there's no reason we couldn't do 5 squared plus a number times 5 plus 1 equals 0. There's no difference as far as the math is concerned, I think. Why is the discriminant a perfect square? That is curious. I assume it has to be for there to only be 2 solutions. I guess there's 4 solutions because it's quartic. But with a plus or minus there, I think I assume there's a reason that it has to be. Yeah, and so you would need to check these manually, I guess, but Papadoria says he knows that. Same culp. We can think about that after. Jasu's concern is line 3. As in that line. Well, yeah, that's kind of the big step, I guess. Um, yeah, um, I don't know. Yeah, I don't see why you couldn't. Um, I wonder if you could. The thing I'm wondering is like, can we know which solutions are right and wrong? I feel like it could be so useful. This is still a lot of work, I guess. I don't know. Maybe. Papadoria just cooks. I don't know. Papadoria is known for bringing some crazy problems. This doesn't surprise me. Oh, this. Oh wow, that's a short album. Or time is flying. 47 minutes. Dang, I wasn't able to, I wasn't really paying full attention to be honest, but for the songs that I was paying more attention to, it's not bad. To have a whiplash change of music pace here. Let me bring in Sandkalp's question. Yeah, it's a funny idea. How did he get line 3 from line 2? Um, it's the quadratic formula, but instead of x, we have 5. And so the a here is 1. The b involves x's, negative 2x squared minus 1. The c is x to the fourth plus x. If you involve an x to the fifth, I mean, I wonder like what powers of x this would work for. Because this does turn out nicely with the discriminant being a perfect square. If that wasn't true, this could get a lot uglier. Depressed planet, a small recap of similar triangles. Similar triangles have all the same angles. And so they're really like fundamentally the same triangle. All you can really do is scale it up or down or rotate it. Hey, Aaron. Yeah, like actually, I shouldn't say that. Yeah, when all the angles of a triangle are the same, it has to look basically the same. We'd say that the sides are in ratio. Um, yeah, I guess I'm not sure exactly what you want to hear about. Like, there's a lot of things I could say about similar triangles, but they're fundamentally the same triangle, just scaled up or scaled down. And that scaling means the sides are proportional. And so yeah, but yeah, so x is just a number. That's why I think it's okay, or it can be okay at least. No worries, Depressed Planet. So we're only when the quartic is factored to a biquadratic. Yeah, that's the thing, Krim. Like this wouldn't always come out cleanly because you do want it to be a perfect square. I think otherwise you're in for a world of hurt. You're not actually going to save any time. Yeah, Papadoria. I think it's just a luck thing or something. I don't know. Or the fact that it has clean solutions means it wouldn't. It would have to have. It would have to be a perfect square in order for the original thing to have clean enough solutions. I think. So this feels like a combinatorics question. If we choose, we can freely choose any 2 points, distinct points. Only the third point is restricted. because we could choose, say, that point. We can choose this point, and the only wrong answers lie along that line for the third point. And whatever we do, we should divide it by 3 to account for rotations of, or like for the repetitions. It's 190. Pick's theorem. I haven't heard of that. I don't think. "19 times 20 divided by 2," Krim says. Because for the third point, um, I don't know. Krim is saying it's this. I couldn't tell you why. There's 2 people saying 190. What is Pick's theorem? Oh, is that literally the exact thing? Some integers from 1 to 19? That's crazy, $10. I couldn't tell you why. Leave the square root of the diagonal 21 elements multiplied by 0.5. I'm not sure. Would I be the thing we want, though, Papadoria? For points to be inside, the point should lie to the line x plus y equals 21. Sure. I'm sorry, none of these explanations make sense to me. Oh, we can't be on the boundary? I didn't realize that. Why is that 119 and not 121? Or not 120? Oh, because that's on the boundary, I guess. Okay, I can see how this is becoming like triangular numbers, like Pascal's pyramid here. Why does that? Why would the sum of integers from 1 to 19 give the number of triangles you can make? I don't know. I oh my gosh, excuse me. I think I'm getting tired, to be honest. I don't see why it's just the number of green dots inside the triangle, though, I guess. Because those are just all the options of points we have available. I don't like we if we choose 2 points though, we can't choose any other point we want. Wait. Oh my god, did I misread the question? I'm just fucking stupid. Oh my god. I misread the question. Okay. Yeah. It's way simpler than I thought. I thought you had to make triangles inside of this triangle. Uh, all right. Fuck it. I'm ending stream. I clearly can't think. Uh, yeah. Sorry, but I'm fucking I'm mad at myself. Yeah. Sorry, but yeah. I'll see you. I'll see people here on YouTube. Thanks for being here. I'm on Twitch. We're gonna look for a raid, but yeah, Papadoria, Sandculp, Crim, Inosis here. Thanks for being here. Yeah.